That's excellent. Thank you very much indeed. So this is a story that goes back a long time. This is not, I'm afraid, about first passage percolation. I once dabbled in first passage percolation, but it was many years ago, and I haven't been active in that area since. So this is about classical percolation, about which I'm sure the audience is informed, though I will quickly review it. And it's about the obvious question. I mean, the obvious question is, what is the value of the critical point? And the obvious answer is, except in special cases, we'll never know. And this lecture is about special cases, but it turns out that there are a countable infinity of special cases, and that's a very special thing. So percolation thresholds, we're discussing here percolation thresholds of bond and site models. So part of the lecture will be devoted to percolation, then there'll be a section on bond models, then there'll be a section on site models. Now, let me just remind you, and I know I can do this very quickly, we take a lattice. So one natural question that everybody should be asking is, what is a lattice? And the answer is, I'm not going to tell you, but it's going to be it's going to be a reasonable thing. And of course, I remember a lecturer once explaining that the square lattice is the probabilist's best friend. Actually, of course, that's not really true. It's only a certain type of probabilist that considers the square lattice to be their best friend, and certainly I'm one of them. So the square lattice is drawn here. To think about a lattice as a very a graph drawn in finite dimensional space in a reasonable way, whatever reasonable means, we might come to that later, with a large automorphism group, such as an automorphism group which acts like Z2. So translations by certain multiples, rightwards or upwards, preserve the graph. But of course, really a lattice could be described geometrically, it could also be described algebraically, it can be described combinatorially. And so the question, what is a lattice, is really an interesting lecture in its own right. But think the square lattice, but of course things will get more general later. So in the site model, in the bond model, or the edge model, we inspect each edge and we flip a coin to determine whether that edge is in state 0 or in state 1. There are two possible states for every edge, and edges receive states, and the states are IID random variables. So you flip a coin for each edge. If the coin comes up heads, you declare the edge state 1, which we call open in this universe, open to the passage of fluid. So this guy here got state 1, this guy here got state 0. So this edge is open, this edge is closed, and we look at, now we supply liquid at the origin, or infection, or a voting habit of some sort, and that flows down the open edges, and it infects or reaches this set of vertices, but water coming in at 0, the origin does not infect this set. So these are the clusters, the open clusters of the bond percolation model. The site model, we do the same with the sites. So instead of declaring the bonds or the edges to be open, we declare the sites to be open or closed, and then the material flows through the open sites only. So that's the model. It goes back at least as far as Broadbent and Hammersley, and it has been. John Hammersley worked very hard on it for many years. And he had some difficulties which we're about to come to. Then there have been periods of quiescence in the basic theory of percolation. There have been also theorems of at times of great activity. And the last 20 years has been a period of enormous activity for two-dimensional percolation, but not for general percolation in 2 dimensions. So 2 dimensions is special, and we're going to see that. So the big picture is, you start with you look at the open connections, you say X is connected to Y if there's an open path from X to Y, a path of open edges or a path of open sites for the site model. And we're interested in these connections. These connections, and this is the connectivity relation of the open graph. And we're interested in whether or not there's an infinite cluster. If you supply water at the origin, does it reach infinitely many vertices? So we declare the probability of that to be theta of P. So theta of P is the probability that the origin has an open path which stretches to infinity. It's an infinite open path. And when we plot theta of P, it looks roughly like this. So when P is sufficiently small, theta is 0. When P is sufficiently large, theta is strictly positive. It's pretty obvious that theta is non-decreasing. If you increase p, remember p is the density of open edges or the density of open sites. It's the probability the coin comes up heads. If you make the coin come up heads more often, then you make more sites open or more edges open, and so you increase the chance of an infinite connection by monotonicity. And so theta has to be non-decreasing. And we believe in general, remember I haven't told you the number of dimensions yet, we believe in general that theta looks like this. Now, but this picture is very deceptive because it communicates, excuse me, let me just close the window. Because it communicates some facts which are not proven. It looks like, well, first of all, the first statement is, by monotonicity, there exists a critical point, a PC, which separates the zero phase from the strictly positive phase. It looks as if theta is very smooth up here, and we now know that because of recent, in general dimensions, because of work of Georgiakopoulos and Panagiotis, that the theta is real analytic on the interval PC1 for all dimensions. It looks like I've drawn a concave function. Well, it's not generally concave. I mean, it depends on the lattice. Funny things can happen here to prove that it's not necessarily concave. But I have drawn it as if it's concave because that's what the physicists thought for quite a time. But I think you can construct examples which are not concave over the whole interval. It may be concave in an interval just to the right of PC. And I've drawn it as if it's continuous at PC. So it's real analytic above PC, but it may be in general be discontinuous at PC. So the obvious question is, you describe this to somebody in the street, and they say, but what is PC? So in the case of the square lattice, for bond percolation, PC is a half. Ted Harris proved very early on that PC was at least a half. Hammersley did lots of numerical simulations, which produced a prediction of PC of less than a half, and which supports, Hammersley would say, supports the belief that PC equals a half. It was a very big theorem of Harry Keston in 1980 to prove that PC equals a half. So PC equals a half of the square lattice, and moreover, Harris proved that theta of a half is 0. So for the square lattice, PC is a half, and sorry about this, there we go. For the square lattice, PC is a half, and at a half, we have continuity. Theta. So the value of theta at PC determines continuity because theta is automatically continuous from the right. So the question of continuity at PC is equivalent to theta of PC equals 0, continuity at PC, left continuity at PC. Okay, so why is that true? We'll come to that in a moment because we're going to inspect that in greater generality. But the big conjecture, which has been the big conjecture now for in excess of 30 years, is that for either bond or site percolation on any lattice in any dimension, we have that theta at the critical point equals 0. And that's strongly believed. It's known in 2 dimensions because, well, I just stated it for the square lattice. But there are general results in 2 dimensions, general arguments which work in 2 dimensions. And it's known also for the cubic lattice in d dimensions when d is sufficiently large. And the reason is because of what's called the lace expansion, which is a big technology. You have to spend a lot of time to understand it. And it's like driving a very complex vehicle. And once you've learned to drive the vehicle, of course, you insist on driving it because you've invested a lot of time. So at least it used to be a big vehicle. There are now easier ways of learning to drive the lace expansion than there were 10 years ago. But the lace expansion produces an infinite series. It's a kind of discrete Fourier analysis representation of objects you're interested in. It produces an infinite expansion of one of these functions. The question is, when does the series converge? And you can make the series converge by making something small, and that something could be 1 over d. So if you make d, the number of dimensions, large, then it converges and everything goes through. How large? Well, that's a game. How large? Can you do better than the previous people? And the current record is held by Pfitzner and van der Hofstad, who proved this down for d equals 11. This method, the lace expansion, should work down to d equals 7. it probably won't work. Well, it certainly won't work at d equals 6 without some substantial changes, and it shouldn't work at 5, 4, or 3 because the predictions, it predicts more than just this, and the predictions are incorrect for d less than or equal to 5. So there's an exact calculation, which has been really, really very, very vital in the theory of percolation. Now, so exact values. So where do exact values come from? For the Bond model, they come from duality. For the site model, they come from matching. So duality means we take the square lattice, that's the black lattice, we place a vertex in each face, that's these red vertices, and we join two red vertices whenever they correspond to an edge of the black lattice. And of course, you see immediately that the square lattice is self-dual, and it's self-duality that tells you that the critical point is a half. You can, if you have the Bond model on the black lattice, that implies a Bond model on the red lattice by saying the state of this red edge is the converse of the state of the edge that it crosses. So the black percolation model generates a red percolation model, and that duality between percolation model, not just a duality between graphs, it's a duality between measures. The initial measure is a measure with some density p. The new measure on the red graph, well, that's present if and only if the black graph is absent, so that's density 1 minus p. And as p increases, the black graph moves through the critical point and the red graph moves back through the critical point. They have to cross over. So they cross over at p equals 1 minus p, which has the solution p equals a half. That's the quick reason why it's a half. But the proof is longer than that. Now we have easier proofs now than Harry Keston's proof. For site percolation, the picture is slightly different. The corresponding notion to duality is matching. Now, I've chosen a very bad example here. I'm going to give you a better example in the future because this graph, this is the triangular lattice drawn in a rather unusual manner. This graph is self-matching, just as the square lattice is self-dual. So how do you construct them? So let me just state that, leave that at the moment. So I tell you, this graph is self-matching, and because of self-matching, the site critical percolation probabilities are half, for more or less the same reasons as for the Bond model. But what does self-matching mean? Matching pairs. These were introduced by Sykes-Essam in 1964. These results go back a long way. Their paper is a paper in physics. They don't actually prove a great deal, but they indicate a very interesting method, and the method produces extremely interesting, from the point of view of mathematicians, predictions or conjectures. Though Sykes-Essam wouldn't want them to be called conjectures. From their point of view, they're results, they're physical results, and they believe they're true. And in a sense, they are true, and in a sense, they're not true. What's the point? So you start with a graph. Now, this graph I'm going to call a mosaic. It's like a two-dimensional tiling. Think about it as a mosaic, but really it's just a two-dimensional graph. It's plane. By plane, I mean, so a planar graph is a graph that can be drawn in the plane such that edges only cross at vertices. A plane graph is an actual embedding of that graph. And it is a drawing of the graph in the plane with that property. And a given planar graph can have different embeddings. It all depends upon how you embed the, well, you can sit down and play with it. So this is a plane graph, is a planar graph and an embedding. So these are actually plane graphs because I've drawn them in the plane. One-ended. One-ended means, well, it's infinite and it's not infinitely ended. And infinitely ended, things like a tree. I mean, you could take a binary tree and draw it in the plane. It would get very dense as you got further away from the origin, but still it is a plane graph, but it has infinitely many ends, so the number of ends of a graph is so if you delete a finitely many vertices and count the number of infinite components you get left, it's the maximum of that number of infinite components as for over all finite sets being deleted. So if you delete any finite set of vertices of the square lattice, you still only have an infinite cluster, one infinite cluster. If you take a binary tree and delete one vertex, you get 3 trees. If you delete more vertices, you create more and more infinite trees. So the tree is infinitely ended, has infinitely many ends. The square lattice has one end. So all your regular lattices drawn in the plane have one end. So this is not, so we understand ends, and they include all the planar lattices, all the regular planar lattices with reasonable embeddings. Now, transitivity is very important. Transitivity is about automorphisms. So a graph is transitive if given any two vertices, there is an automorphism from the first to the second, which preserves the graph structure. So the graph, essentially, if you take any two vertices, x and y, and I sit at x and you sit at y, the graph I see relative to x is isomorphic to the graph you see relative to y. Transitive means the viewpoint is the same wherever you're standing. Quasi-transitive means just that the automorphism group acts with finitely many orbits. In other words, there is a finite set of vertices, and wherever you are, the graph looks like it looks from one of that finite set of vertices. For example, if you took the square lattice and put a vertex in the middle of each face and joined it up to one of the vertices of the face, so you take the square, and you just add a point in the middle and join it up to one of the vertices at the edge, that's a quasi-transitive graph because there are the original vertices and the new vertices, and they look differently, but there are only two types. Now, so we take this square lattice is fine. Think the square lattice. So F is the set of faces of M. So for the square lattice, it's just a set of squares. Now you partition F as F1 union F2. So some faces are put in F1, some faces are put in F2, but every face is put somewhere. But you make that partition in such a way, see what we're going to do is from F1, we're going to construct a graph, and that'll be the graph G1. So we get G1 by taking the original graph M and adding all diagonals to all faces in F1. So if a square, for example, of Z2 is in F1, you add two diagonals to it. There are two diagonals to that square. And you do that to all faces in F1, you get G2 by doing the same to F2. You want G1 and G2 to continue to be quasi-transitive. You don't want to do this, randomly according to, the binary expansion of pi or anything. So we're going to decide, I insist that my partition has a property of quasi-transitivity, whatever that means. That gives us two graphs, G1 and G2, and we call them a matching pair. Notice they're not planar, because if I take a square and add two diagonals, it ceases to be a planar graph. And if I have a hexagon and add all the diagonals to it, then of course it's even less planar, if you see what I mean. We have these matching pairs. Here are two examples. I started with the square lattice, the mosaic, the square lattice, and I took a 3x3 grid of faces here, and I declared these faces to be in F1, and the other faces, that's these faces, to be in F2. And then I tile the plane with copies of this. I tile the square lattice with copies of this. So this is now, these are examples. If I call this infinite graph G1, this G2, that's an example of a matching pair. Okay. A more extreme example would be to take F1 to be the empty set. Then I'd look at the original square lattice. Then F2 would be there have to be all squares, in which case my matching graph would look like this. So this is a pair G1 and G2, except this is really the original mosaic M, and this is called the matching graph of M. So this is a definition of the matching graph of M, called it M star. So it's the graph M with all the diagonals added. Now these are matching pairs, and Sykes-Essam did some calculations. And Sykes-Essam and the bond parallel lead to the following statement: that generically, if you take any graph G, and any plane graph G, and it's dual, and that's G is plane. Remember, G plus it's the dual graph of G. That's also plane. Then their critical probabilities add up to 1. So if G plus is a dual pair, the critical points in bond percolation add up to 1. And that, of course, that's equivalent for the square lattice to say PC of the square lattice is a half. For the site model, if you take any matching pair, then the critical points add up to 1. That's what Sykes-Essam wrote. Both those statements are sometimes true and sometimes false. They're true. I'll tell you the answer. I mean, Sykes-Essam would say, well, it's true. What we did is true. We just never thought of your example. And that's true. The point is that when I talk about plane graphs, I talk about graphs embedded in the plane. But for example, the binary tree isn't one-ended, but you can add edges to it. You can decorate it to make it a one-ended graph. That's a plane graph, but it becomes denser and denser as you move out to the boundary of the plane. So the natural embedding of the binary tree is not in the Euclidean plane; it's in the hyperbolic plane. And so it actually turns out that these statements are true in the Euclid if the embedding is a reasonable embedding in the Euclidean plane. But if the reasonable embedding is in the hyperbolic non-Euclidean plane, then they're false, and I'm going to explain that. So the idea of the proof I've already mentioned. I won't go into that in detail here, but I will just make a serious point which has to be understood in the proofs. We're talking here about embeddings of graphs in the plane. What are the properties of embedded graphs? How do we embed graphs in a plane? Is there any particular, for general graphs, for general mosaics, and they can look pretty peculiar, some of them, there may be more than one embedding in the plane. Is it important we pick a particular embedding in the plane? And which plane? Is it the Euclidean plane or the hyperbolic plane? So there are theorems of many people involved in planar embeddings of graphs. It's a piece of topology stroke combinatorics, very beautiful. We understand a lot about it. It's connected to circle packings and things that probabilists are interested in. The obvious name to associate with some of these embeddings theorems is that of Laszlo Babai, but a number of people have worked in this area. I want to show you the Sykes-Essam argument because we don't know how to make it true. Sykes and Essam, in one page or half a page, one transparency, proved, in a sense, their statement, but we still cannot make, although we know the statement is now true, or when it's true, we can't make sense of the theorem. So take a planar graph, gamma. So gamma is so I take take a general planar graph, vertex set V, edge set E, embedded in the plane. It's a finite graph. There's going to be a finite graph to start with, then we pass to a limit. And I count the number of faces, that's F, and I count the number of its components, that's K. Then the famous Euler's formula is that, and you can prove it by guesswork or by induction on something. It's very simple, but it's a very useful formula. So now, if we apply this Euler's formula to this graph, leave the F for the moment. V is the vertex set of gamma. So I'll use V to mean its cardinality as well as its set. That's the number of vertices of gamma. This is the number of edges of gamma. That's the number of components of gamma plus 1. What's the number of faces of gamma? Supposing I went to the dual. Every face, there's a one in the dual, there's a one-to-one correspondence between faces of gamma and components of the dual. This isn't completely clear from the way I set it up here, but we're going to see an application in a moment. I haven't laid it all down in detail here because I don't want to spend time on it. But basically, when I move to the dual, that number of faces becomes the number of components of the dual. Now I take my gamma to be a special gamma. So I define gamma. I think I've got my notation here wrong, but let's carry on. I want gamma to be, I want now to take bond percolation. I'm going to do bond percolation, not site percolation. Their paper applies to bond percolation as well. I want to take I've got the lattice G. So think of G as the square lattice or whatever lattice you like. Take a box. I have to take a box because I want to move to the infinite volume limit. Look at the open subgraph and call that gamma. Now, I take the number of clusters of gamma. The function I want to consider is I take the number of clusters of gamma, that's the number of open clusters, divide by the number of vertices, and let the number of vertices tend to infinity. So that's the infinite volume limit I'm going to take. When I do that, what do I do here? Well, I divide through by the number of vertices of gamma, and I send that number of vertices to infinity. And I get on the left something involving the number of clusters of the dual, and on the right, I get the number of clusters of the primal. And everything else is well behaved. I divide this by the number of vertices and pass to the limit, I get 1. I divide this by the number of vertices and pass to the limit, I get the average number of edges per vertex, which is a constant. No, it's not an average number of open edges per vertex, but it's a very smooth function of P. So when I do that, I get this guy turns into the kappa function of the dual graph at 1 minus P. I put a suffix here in there here. And here on the right-hand side, I get kappa of the original graph, and I'll pull that over to the left-hand side and pull everything else over to the right-hand side. And I deduce that C is because the vertex counts in the graph and its dual graph may be different. So I end up with the left-hand function this difference is a polynomial in P. So kappa is called the number of clusters per vertex, or in physics, it's called the free energy. So this is a polynomial in P. And that just comes from Euler's formula. Now let's make an assumption. Let's assume that kappa of G at P has a unique singularity viewed as a function of P. It's well behaved when P is less than PC. It's well behaved when P is bigger than PC. These are nice phases, but at PC it has a singularity. Singularity means a point when it is not infinitely differentiable, a singularity. So, and the physics tells us that PC is a singularity. Everything is singular at PC. Everything reasonable is singular, but everything is smooth away from PC. So this function, the right-hand side, is a polynomial in P, and that's smooth for all P. But this has got a singularity at PC, and this has a singularity at PC. So those two singularities have to cancel each other out to create something which doesn't have a singularity, which means that the singularity of the left function, which happens at 1 minus PC, is the same point as the singularity of the right function, which is at PC, sorry, 1 minus PC of the dual graph, a PC of G. So you think it through and you end up with the formula you want. This is fundamental. I don't want to get, it'd be a mistake to get too involved in the details. This is the idea of the Sykes-Essam prediction. And we don't know how to make this argument work. The first problem is kappa is well defined, but we don't know how to prove that it has a singularity at PC. We cannot eliminate the possibility at the moment that it's infinitely differentiable at PC. We don't know how to do that, even in 2 dimensions. And the conjecture which comes from physics is that the nature of the singularity is very, very specific in 2 dimensions, that the third derivative, it's twice differentiable. I think we know that. I think Harry proved that. But its third derivative at PC the third derivative does not exist at PC. And in fact, near PC, it behaves like P minus PC to the minus a third. So it blows up at P equals PC. But the way we write this is P minus PC minus 1 minus alpha, where alpha is a critical exponent. And the belief is that alpha is minus 2/3. So that's the challenge. Make sense of the Sykes-Essam argument from 1964. Let's move on to bond percolation. In bond percolation, then, we have we can compute critical values sometimes, but we can also find what I call critical relations, exact relations between critical points. Here's an example. Take the triangular lattice and the hexagonal lattice. The triangular lattice is the red graph, the hexagonal lattice is the black graph. They form a dual pair, so their critical points add. Right, we know how to prove that. We've known for a long time, actually, since a couple of years after Harry Keston's proof. John Riemann used Harry's method to prove that for this pair. But there are 2 values here, and we don't know the values. So if we're going to find the values out, we need another relation. And that relation, of course, is the famous star triangle transformation, which was discovered by Kennelly in about 1899. I like calling it the YDelta transformation because it looks nice, but of course it's normally called star delta, star triangle. You know, it's got a number of names, but they all mean the same thing. He discovered this for electrical networks. For bond percolation, it's the following. And by the way, it's the beginning of what's called the Yang-Baxter equation in mathematical physics. To take a triangle, quickly, take a triangle with 3 different probabilities on the edges. Replace the triangle by a star. So you put a new vertex in the middle and join it up. But the probabilities change. I'm going to do it in the following way. Here's P0. This edge corresponds to this edge. We'll give that 1 minus P0. We do that around the triangle. Okay. Then the observation is, what you're interested in is connectivity. Supposing I've got a path coming in here, an open path that comes into A, and goes down here and then goes down to B. But I'm interested then in the probability that A and B are connected in this triangle. So connectivity within the triangle is a binary relation. A can be connected to B, B can be connected to C, and so on. If A is connected to B and B is connected to C, then A is connected to C. So it's a binary relation on the vertices. The connectivity here then, and the probability of connectivity, the measure of that binary relation is given in terms of the triple P0, P1, P2. Same thing over here. Connectivity between A, B, and C is a function of P0, P1, P2. And the observation is that the connectivity measures are the same if and only if a function kappa, this is a different function from the last slide, a certain function kappa of those variables equals 0, and that function is that. That's a trivial piece of first-year probability. You just compute the probabilities, and we check that they're equal if and only if that equation involving kappa is true. So that means that if you if you have a big complex graph with a triangle in it, you can and the P0, P1, P2 satisfy this equation, then you can replace the triangle by the star with the appropriate values of P. And nobody else can tell the difference. Of course, there's a corresponding version for electrical networks. That's now classical, of course, 123 years old. There's also a version for Potts models and Ising models. And indeed, the Yang-Baxter equation is one of the fundamental techniques of the geometry of mathematical physics in 2 dimensions. Now, it follows then from this little computation, if you think it through, if we set all these p's equal to little p, then kappa p p p is 3p minus p cubed minus 1. And if that's 0, then you can turn the triangular lattice all the triangles of the triangular lattice, well, actually every other one is turned into one of these guys. And then, of course, if you do that to this triangular, that's not a good picture, sorry. Then the triangular, if you replace this one by the star and you do that to every other triangle, then you get another star up here, you get another star here, then you get a hexagonal lattice. It's different from this construction. It's another construction that maps the triangular lattice into the hexagonal lattice. And from that, you find that the root of this equation is the critical point of bond percolation on the triangular lattice. So what have we observed? Because of duality, there is a relation. Because of the star triangle transformation, that's an extra relation, which in some cases, including this pair, provides the other answer. This provides the other relation, which tells you how to compute critical values. Now, all this is I'm now going to tell you how far you can push this argument. This goes back to, it's about 10 years old, this work. It's joint with Ioan Manolescu. And I'm going to show you very quickly how it works, because I think it's extremely beautiful. And it turns out to have many applications in other areas of mathematical physics. I mean, it's not only in percolation that this works. This works more or less whenever you're working on a type of graph called an isoradial graph. What is an isoradial graph? So the red graph is isoradial because each face, here's a face, has a circumcircle, and each face has a circumcircle, and all those circumcircles have equal radius, isoradial. So a graph is isoradial when embedded in the plane. If every face has a circumcircle, it's convex, every face is convex and it has a circumcircle, and all those radii are the same. Now, let me just note a formula that the first thing to notice is that if this circumcircle has a center, this circumcircle has a center. So it's natural to take these two centers of there's an edge here, concentrate on the edge. The edge corresponds to two circumcircles, this one and this one. They have centers, and we add these black edges to the endpoints of the edge. That black figure is a rhombus. It's a parallelogram with equal sides. In fact, the equal sides are, the length of the sides is exactly equal to the radius of the circumcircles. So the geometry of that rhombus is specified by this angle, call it theta. So this is the edge E, this is the angle theta E. So the measure to remember, we're going to do bond percolation, is that P associated with this edge is something, PE, and PE is given in terms of theta by that formula. Why that formula, I'll tell you in a moment. But there is, except that if you take an isoradial graph, plot these rhombi, compute these angles, and that'll tell you the value of P to put on that edge. Okay, so the isoradial G gives rise to a bond percolation measure, which I'm calling PG. It's a sort of canonical measure defined, which comes out of the geometry of the embedding. Now, if I go to the dual graph, the dual graph is on the, so this face has a vertex in its dual, inside it. I'll take the centers. So I take the centers of the circumcircles as the dual vertices. So this edge then has there's a dual edge between these two dual vertices. And of course, that's also an isoradial graph, and we'll see in a moment why, actually. And that isoradial graph then has a dual percolation measure, in fact, the value of this is exactly 1 minus the value of this. And that's because theta of E becomes pi minus theta of E, and that switches 1 to the top. So PE becomes 1 minus PE. So you see how that works. Isoradiographs in this context were introduced by Kenyon, and Kenyon wrote down this formula. I want to show you about rhombic tilings. Rhombic tilings are very beautiful. I was able to lecture about rhombic tilings to school children in Oxford recently. And that's very nice because, of course, they have the Penrose tiling on the ground outside, on the terrace outside the entrance to the Wiles building in Oxford. A rhombic tiling then is just a tiling of the plane by rhombi. So this black graph here is a bit of a rhombic tiling. There's a nice rhombus. There's a sort of flat rhombus. There's a pretty square rhombus. All these rhombi are different in geometry in principle, and I can continue this forever, or well, let's assume I can continue this forever. And so there's a rhombic tiling. A rhombic tiling is a bipartite graph in the sense that if I fix a vertex, supposing I fix this vertex, color it red, I color the opposite vertex red, the opposite vertex red, opposite in the rhombi, opposite, 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 carry on in this way, then I obtain one of these isoradial graphs. And if I look at the other vertices, the white vertices, I do the same to that and join that to the opposite, to the opposite, and to the opposite, and to the opposite, I get the dual of the red graph, and that's also isoradial. So a rhombic tiling generates 2 isoradial graphs, a dual pair of isoradial graphs. Rhombic tilings were introduced to this field by Duffin in a famous paper in 1968. He showed that these are the right places to work with discrete holomorphic functions. So analytic functions, holomorphic functions are in the continuum, the complex plane, but let's introduce a discrete version. The right way to introduce a discrete holomorphic function is to start on an isoradial graph and then to work with discrete Cauchy-Riemann equations. Now, the other thing you can do with the rhombic tiling is you can draw what de Bruijn, there are very, very beautiful theorems of de Bruijn from the early 80s. You can draw what he calls train tracks, and this is very important too. So here's the rhombic tiling, same rhombic tiling. So I decide I'm going to cross this edge. I'm a train, I'm a railway engine. I cross this edge and I go across to the opposite edge. Now I carry on, I always cross the opposite edge. Always cross the opposite edge, opposite edge, opposite edge, opposite edge, and I construct this path across the graph. It's a train because, of course, this is the left rail of the engine, this is the right rail of the engine. They're also called rapidity lines in physics literature. And I can do this, I can start anywhere. I mean, I can start here and do that, and I get a crossing. I get a crossing. If I do there, I cross both the original train tracks. So a rhombic tiling generates isoradial graphs. It also generates a picture of the train tracks. I can now take the rhombic tiling away and just keep the train tracks, and it's a rather complicated picture. And this is an example. This is a bit of the Penrose tiling. It's a bit of the classic Penrose tiling. The red graph is one of the isoradial graphs you get from it. Now we're going to take the Penrose tiling away. So here's the red graph. That's the isoradial graph. That's to remind you that it's isoradial. This is its train track system. Very complicated, wiggly lines, but not really so complicated as it looks, because I colored them. I've colored each line with one of 5 colors. The blue lines form a doubly infinite set of lines which never intersect. They go roughly from top to bottom. The red lines go from bottom right to top left, and they also never intersect. Similarly, the yellow lines, the green lines, and the gray lines. So there are 5 types of line there, and that's the sort of the 5 dimensions which de Bruijn observed for general constructions of Penrose tilings, the continuum of Penrose tilings, actually. And it's in that sense that we say that the Penrose tiling, that's one of the senses in which we say the Penrose tiling is quasi-periodic, but it's not periodic. There's no translation or rotation or reflection of the Penrose tiling that preserves it. So here are examples of track systems. The square lattice, of course, well, you take the track system. It turns out I've straightened out the tracks, by the way, to make these pictures more intelligible. The square lattice track system is isomorphic to the square lattice. I mean, it seems whatever you do to the square lattice, you always get the square lattice. That's not true, of course. The Penrose tiling has it looks like 5 sets of parallel lines which are intersecting each other. And to do what we want to do, you need some properties, but it doesn't. I don't want to emphasize the properties. I'm just saying that there are some regularity properties. But I want to look at the set of all isoradial graphs with these properties, and I call that script G. So script G, think about it as a set of all isoradial graphs with regularity. Then here's the theorem. First of all, that remember these canonical measures. The canonical measure that I defined already is critical. That is the critical surface of G, of the isoradial graph G. That means that if I increase all the P's a little bit, I get an infinite cluster. If I decrease them all a little bit in a certain way, I get no infinite cluster. So if that little bit were a parameter, as the parameter moves through sort of zero, which corresponds to the critical surface itself, that is the critical function, the critical surface of the isoradial graph. Of course, the square lattice is a very regular isoradial graph, and that's equivalent to saying that P equals a half of the square lattice. To prove this, we use a property. Some of you would have come across what's called the box crossing technique. And the point is that the first thing that you have to show is that these measures have the box crossing property. And then you can wheel out all the technology associated with box crossings to prove criticality. You can actually prove much more than criticality. So, you can prove that script G is a universality class, which means that, you see, the critical point to physicists is a collection of exponents, the critical exponents. Functions have singularities at critical points. For example, the probability that the cluster at size, at a given vertex, the origin, has size n, decays like a power law. It doesn't decay like an exponential function. And that power law gives you some delta. And so there are these critical exponents in the way in which those functions behave at the critical value. There are other critical exponents which tell you what happens near the critical value, whole set of critical exponents. And the theorem says that these G are universality class in the sense that we can't deal with all critical exponents, but a big family of critical exponents are identical. They're constant across G. Whichever isoradial graph you pick, you get the same numerical value of that critical exponent. The only problem is we can't prove the critical exponents exist. We don't have a proof of the existence of critical exponents for any non-trivial bond percolation model. So this is a very conditional statement. If we could prove critical exponents existed, for example, for the square lattice, which everybody believes, then they would be the same values for all isoradial graphs.
Geoffrey?
Please.
Aren't they known for the triangular lattice?
Well, they're known for the. I'm about to come on to that actually. So I'll answer that question in a moment. So, but in order to commit myself to the statement, I say again that for the bond model, we don't know of any existence for any bond model, including on the bond model on the triangular lattice. Now, the site model is a different story. So this is what your question is about. For the site percolation on the triangular lattice, we know an awful lot, of course, because we have exact values, we have conformality, we have SLE. This is one of the examples that caused the creation by Riddhipratim of SLE, one of his canonical examples. We know an awful lot about this, and this, of course, is connected to conformal field theory and is answering problems in physics, but it is restricted, essentially, subject to minor perturbations, to the site percolation model on the triangular lattice. So for that system, we know an awful lot. We know essentially all the critical values of the critical exponents. By the way, the one critical exponent we don't know about is this guy. It's alpha. So that's one of the main critical exponents that we don't know about for the site percolation model on the triangular lattice. It's just, I don't know whether it's permissible to use this expression these days, but alpha is just a very naughty boy. It's very difficult to pin down. Partly because you have to go to the third derivative of function to be able to locate the alpha. But for some reason, it's difficult to find out about alpha. But the other critical exponents we know all about. But of course, we only know about site, whereas for the isoradial graphs, this is an enormous family of graphs. And if one of them is well-behaved, say, then they're all well-behaved. Whereas site percolation on the triangular lattice is the opposite picture. We know everything about one of them and nothing about any of the others, essentially. The curious complementarity. Notice a question there, which I'll come back to. When can you turn a bond model into a site model? When can you turn a site model into a bond model? I'll come back to that later. What's special? I'm going to back to bond now. Just to tell you what's special about isoradial graphs. Supposing you have these three rhombi forming what looks like a cube, then this is the isoradial section that you see. You see a star. Now, this star, sorry, I see a triangle. So you see a triangle. I'm now going to do the star triangle transformation. I'm going to replace this triangle by this star, and I do that by moving these squares around. I find there is a vertex in this configuration, a new point, which I call O, such that when I make the star triangle transformation, I end up with three rhombi. These three rhombi become these three rhombi, and the star triangle transformation maps this triangle to this star, and it is a property of isoradial graphs and the function which I stated, the PE function, that if I do this, the connectivity within this triangle is the same as the connectivity relation within this star. So if I make this change of rhombi, I do not change the connectivity. So this is a way, and think about this in tracks. Here I've got this track picture here like this vertical track here I've distinguished from the others by making it black. Whereas in this new track system, I've moved this track to the right of this intersection. So I've made, in diagrammatical representation, I've moved the black track over the intersection to this guy here. So the meaning of this is if we work in track space, there are transitions that we can make which preserve the probabilities of long-range connections. So I have a mapping on track space, which makes I can turn my track picture into another track picture without changing the long-range properties of the corresponding percolation system. And so that gives you ways of, you have to use this mapping, and you use this mapping progressively. These are roughly pictures of the sort of transformations that you make. So these are progressive sequences of transformations using sets of star triangle transformations in track space, and they enable you to take long open paths and to turn them into other long open paths which cross long boxes. So this is the way you prove that the box crossing property is preserved across this family of isoradial graphs. It's a complicated story. This is very much a simplistic explanation. But the conclusion of this story is that Bond percolation on this very large family of isoradial graphs, there is a canonical embedding, which is critical, and this family of graphs is a universality class. For the site model on this unique triangle, unique lattice, though I mean there are minor perturbations where you can get some information, you have an enormous amount. You have exact existence of critical exponents, exact values, and limit theorems, beautiful limit theorems. And what we really want to do is establish a connection between the site model on the triangular lattice, which we know everything, and the Bond model on some graph in script G, and we don't know how to do that. That's the problem. And we point out the connection to the work of Hugo Duminil-Copin, who was awarded the Fields Medal a couple of weeks ago. So he of course has written many papers and in teams, and one of his characteristics is very much working with people and supporting people. That's for me a very important property which wasn't really mentioned in the Fields Medal. Of course, the Fields Medal ceremony was for Hugo; it wasn't for his co-authors. But nevertheless, I think it's a very important personal characteristic of Hugo that I recognise greatly and respect enormously. Random cluster. So Potts models, the easy model has 2 spins per vertex. The Potts model has Q spins per vertex. And there's a more general model called the random cluster model, the Fortuyn-Castellane model. And the Fortuyn-Castellane model is like percolation. So this curly bracket is the percolation measure. You recognize it, but you change it by multiplying by Q, which is this Q or some other Q, but Q could between 0 and infinity, some real Q. You raise Q to the number of open components. So this is only well defined on a finite graph. If you've got 3 open components, you multiply by Q cubed. And so that gives you the random cluster measure, which depends upon P and Q. And the random cluster measure is related to the Potts measure with Q, when Q is integer, with Q spin values. So this is a very important and valuable extension of percolation, which leads to beautiful questions which impact upon the fundamental models of mathematical physics and ferromagnetism. And two recent theorems of Duménil, I'm afraid I know M is Emanuelescu, and I could tell you some of the other names, but I might get them. I might make some mistakes unless I can dig deep here. Let's leave that for the moment, the names. Sorry about that. But so there are two theorems of Hugo and his teams and his groups. So take isoradial lattice, omit the word rectangular for the moment, I'm not going to talk to that, and take a value of Q, because we're going to do we're going to use Potts technology or Potts vision, take the value of Q, but Q's got to be between 1 and 4. Q less than 1 is difficult because you don't have positive correlation, and Q equals 4 is a magic value from mathematical physics. We know why. Above 4, the phase transition is different, but between 1 and 4, the phase transitions we should be able to study the phase transitions using a bunch of techniques. One is using what's called the parafermionic observable that led to Stas Smirnov's Fields medal for the Ising model, and other techniques are more probabilistic, and indeed the technology of isoradial graphs. So they prove that for these random cluster measures, and hence for corresponding Potts measures, they prove some criticality and universality, basically extending the techniques that I've shown you for bond percolation. More recently, they prove rotation invariance. Now, I haven't specified what rotation invariance means, and I'm not going to here, but we think about rotation invariance as a step towards conformal invariance. Conformal invariance is invariance under local rotations and dilations. So invariance under global rotations is a step towards conformal invariance. And if we could prove conformal invariance, as we have for percolation of the Ising model, then we would know a great deal more about the Potts model, which is one of the targets of mathematical physics. Good. So that's just an interregnum, as it were. Finally, I wanted to come to more recent work of myself and Zhongyang Li on the site model. Remember Sykes-Essam. Take a matching pair, this pair or that pair. Sykes-Essam produce an argument that their critical site percolation probabilities add up to 1. Now, there's a problem here, which I just mentioned, which I didn't mention before, about the embedding. You see, there can be many embeddings of a graph. I mean, these graphs are embeddable in a unique manner because they're very natural graphs, very simple graphs, where they're actually Archimedean tilings. This is an Archimedean tiling. But there are more complicated planar mosaics which satisfy my conditions, and they can be embedded in a multiplicity of ways. But the embedding changes the set of faces. And so the embedding changes the possibility for matching graphs. So this theorem, which depends upon the matching pair, should depend upon the embedding. But in a sense, it doesn't. In a sense, whatever reasonable embedding you take, in a sense that I'm not going to dig into here, in a sense, whatever reasonable embedding you take, the theorem is true. So we embed M now in a manner which is locally finite. So every compact set contains only finitely many vertices, and we can embed it isometrically in the sense that every graph automorphism of this graph extends to an isometry of the plane. The complexity is that the plane is not necessarily Euclidean, it could be hyperbolic if this graph is non-amenable. If the graph is amenable, it's embeddable in the Euclidean plane in such a way, but if it's not amenable, then it has to be embedded it's non-amenable, it goes into the hyperbolic plane. And I always think this nice picture, this is, of course, we think Escher. Escher, of course, was associated with the Penrose family, so Escher has an involvement with the construction of the Penrose tiling. This is a different Escher embedding here. First of all, you have to keep away from it for obvious reasons. But this is an embedding which gets sort of hyperbolic towards the edges, denser and denser towards the edges. It also gets denser and denser towards the inside. And as is pointed out by somebody else, looking down this hole is like looking down a carbon nanotube, an infinite carbon, one-dimensional carbon nanotube. So what's the correct Sykes-Essam? I have to tell you something, which is that we can define two critical points. There's the PC, which is the point at which there's an infinite cluster. An infinite cluster is created. But on the tree, for example, as PC, on the binary tree, PC is a half. It comes from branching process theory. And when you pass above PC, you create infinite trees. That's the branching process theorem. But in the whole tree, you construct infinitely many of those trees. and they don't necessarily connect. There are with probability 1 infinitely many infinite trees in bond percolation on the binary tree with p bigger than a half. But there is a theorem of Schornmann and Hegstrom-Perez that there is another critical point, Pu, such that above Pu there is almost surely a unique infinite cluster. So let's take it as P starts at 0. As P increases, but less than Pc, the number of infinite open clusters is 0. Now you pass above Pc but less than Pu, you have infinitely many open clusters, and when you pass above Pu, you have 1. So for the binary tree, Pu is 1. You have to get all the way to 1 to have a unique infinite open cluster. But for many other non-amenable graphs, Pu is non-trivial. So you can see all sorts of questions about Pu, which we're not going to discuss here. But the point about Pu that I want to emphasize is it is strictly bigger than Pc if and only if G is non-amenable. And non-amenable in this universe means non-embeddable in the Euclidean plane. You have to use the hyperbolic plane to embed it in a way which is locally finite and isometric. Okay. So we now have 2 critical points, and our theorem says that if you take any matching pair, PC of G1 plus PC of G2 is not necessarily 1. You have to replace the second PC by Pu. And Pu is strictly bigger than Pc if the graph is non-amenable. So actually, Sykes and Essam were correct. They were correct for amenable graphs, for graphs which are embeddable naturally in the Euclidean plane. So for Euclidean graphs, Pc equals Pu, and then this is the Sykes-Essam relation. But for non-amenable graphs, you have to replace Pc here by something different, which is Pu, and this is a different value. So this is the site version. There is a Bond version of this. Of course, Bond version, you don't have the generality that you have of matching graphs. Bond version just says you take a graph and its dual graph. And that was proved by Benyamini and Schramm quite a long time ago. But as you see, the theorem is true in great generality for matching pairs in the site model. Now, I just want to pretty well stop now, but I'll just want to show you, return to this question I asked you earlier. When can Bond models be turned into site models and site models be turned into Bond models? That's key to this understanding conformality. Well, it's one possible key to understanding conformality, and it's key to understanding the site model here. It's classical that if you take a Bond model, you can always construct a site model from it, because you just take the Bond model and you replace every edge by a vertex. Put a vertex in the middle of every edge, and join up two of these new vertices whenever the two edges share a vertex. So you've got 2 edges which share a vertex, they're next to each other, so that material can flow down one and then flow down another. Then these 2 new vertices corresponding to these 2 edges are connected. And then the connectivity is really just the same. And in these 2 new vertices are open or closed depending upon the edge. So every Bond model defines via its covering graph or its line graph a very natural site model. The converse, there are site models which do not come from Bond models. But here's what we do, and this isn't an original idea, but it's the usage which is special. Take a matching pair G1, G2, and take a site configuration omega on G1. So you've got a site model on G1. Now I'm going to look at edges, and I'm going to define a variable on the edges, and I define it to be the product of the site values at the endpoints. So that means that an edge is 1, it's open, if and only if both its endpoints are open in the site model. So now every bond is either open or closed. It's got a 0, 1 value state sitting on it. And so I end up with a beta, which is a configuration of a bond percolation, but it's not an independent bond percolation anymore. It's a one-dependent bond model, because an endpoint U in general is the endpoint of many edges. And so the state of U as a site affects the states of all those edges. So this is a one-dependent bond model. So you have to work with, instead of independent regular percolation, you have a one-dependent model, and that introduces some difficulties. So I'll close in a minute, but I just want to show you a couple of pictures. So the key observation, there is a key observation in relating the site model on G1 to this one-dependent bond model on G1. That's triviality. Harder is to work with the site model on the matching graph, which comes from omega. So I have an omega on G1, that gives me an omega bar on G2. So I want to count the number of infinite clusters, relate that to the number of infinite clusters in the dual of G1 with the dual configuration of beta. So I'm introducing objects without giving you the time to absorb them, but I'm telling you basically there are 4 counts that you need to do. And the main technique is to prove this equality. And this picture, which I'll tell you about if you ask about it, but if you don't ask about it, I won't. This picture is a proof of that equality. Basically, this picture starts with, you start with the face of the primal graph. You notice that the face, well, I think I'm not going to do it. I think I'm going to stop. I think I'm going to stop and say, this is the picture that proves the theorem. And I think that's an appropriate point to stop, if you'll permit me. Thank you very much.
Are there any questions for Geoffrey? So I have a couple of questions.
Thank you.
Maybe it's not directly about your talk, but you'd mentioned the Yang-Baxter equations. And we've been hearing a lot about solvable models in first and last passage percolation. So it's often been mentioned that somehow these Yang-Baxter equations classify all of these solvable models in first and last passage percolation. Is there an easy way or a quick way to understand why that is?
So I don't even know enough about the current position with first and last passage percolation. So there are these expressions which come out of mathematical physics. So this is my very crude take on it, and I don't know the answer to your question, by the way. My very crude take on it is that there are words like solvable. There are expressions like Yang-Baxter equations, and physicists use these expressions, but of course there is some ambiguity in their interpretation to mathematicians, because we want to understand what these words mean. We want words to have meanings, to have definitions. You know, the value of a definition is enormous. That's really, in a sense, what distinguishes mathematicians from non-mathematicians. So solvable is a word, of course, used to mean that you can do some exact computations for a given model. The Yang-Baxter equation is a rather general algebraic structure, which started with the star triangle transformation, but has grown much further into a piece of pure mathematics, which I don't understand, which I try to understand, but is not but I've decided to spend my time doing other things, which lead sometimes to certain exact calculations. So, for example, I try not to use the word Yang-Baxter equation when I talk about isoradial graphs, because really it's just the star triangle transformation. It's just our old friend. It really only becomes Yang-Baxter when you move into this general algebraic structure. And a nice way of representing that a part of that general algebraic structure is precisely in these operations on train tracks. That's the sort of primary elemental transformation that works in this universe of Yang-Baxter equations. So whether or not, now I'm out of my depth, because I don't know whether there is a piece of mathematics which uses a Yang-Baxter relation to solve the last passage or first passage percolation, well, last passage percolation problem. And that's up to you chaps, I think, to tell me. So I don't have a simple explanation, but that's my sort of pick. That's what I tell PhD students. So the notion of solvability does not necessarily mean that it's automatic that there's a Yang-Baxter equation explanation.
We have another question from Eric.
So you've told us about our belief about what happens at PC. In the non-amenable case, do we have beliefs about what happens at PU?
So this question has been explored but not at the level of phase transition. I mean, so one of the questions about PU, of course, is what happens at PU? Is there a unique infinite cluster at PU or not? And there are numerous theorems in the literature which I've not been following, which answer, and I don't know which answer that question. I don't know whether that question is completely answered. Now, but you imply another question, I guess, which is what happens to macroscopic functions at PU? Do they have points? Do they have singularities at PU? I think I don't know. I think one would need to ask somebody like Tom Hutchcroft that question. But I don't believe it's something. There is no established literature on that question. But there may be one or two papers that I don't know.
Okay, thank you.
There's a question online in the chat. If you can check from
Oh yes, thank you. So let me just pull up my chat. Is there any easy or intuitive explanation of the equation PC plus PU equals 1? Well, imagine you have this matching pair G1, G2, and take P originally to be small. So when P is small, of course, G1 is going to be subcritical. And now the corresponding site model on G2, instead of having the value P, how do we do it? So I'm stuck between colors and numbers here. So in G1, we have open sites and closed sites, open with probability P. So in G2, the natural model to look at is I declare a vertex, a site to be open in the G2, and even though it's closed in G1. So effectively G2 is a site model with parameter 1 minus P. So when P is small, G1 will be subcritical and G2 will be heavily supercritical. It'll be above PU, so it'll be a unique infinite cluster. Now P increases. As P increases, the statement you have to prove is that as P passes through PC of G1, so that's the point at which G1 has a phase transition and an infinite cluster is created, then 1 minus P, which we're now looking at G2, is decreasing, and that passes through its first critical point, which is at PU. So as an infinite cluster is created at PC of G1, an infinity of infinite clusters is created in G1. As the dual process, that's 1 minus P, decreases, it ceases to have a unique infinite cluster, and it moves into the phase of having infinitely many clusters. And as P continues to increase, it moves through PU of G1, which means that all these infinite clusters weld together into a single unit. And at that point, the infinite cluster of the dual disappears. So the point is that both G1 and G2 have two critical values, and these two critical values are mapped onto each other by this relation. If in another picture, if these critical values were different, then there might be a phase, for example, in which G1 has a unique infinite cluster, but G2 has infinitely many infinite clusters. And that can't happen because the infinite cluster of G1 sort of goes everywhere and blocks everything off. So you can't have a unique cluster in one graph with an infinitely many clusters in the other. And that's what you have to prove. So I think that's the intuitive explanation, and I think it's easy. It's just not so easy without a blackboard. With a blackboard, of course, it would be easier to write it down.
Are there any other questions? If not, let's thank Geoffrey again.
Thank you very much for your hospitality, everybody. Have a lovely time for the rest of your meeting.